Okay, so here we have the next question on the menu today, and the question is asking us linear versus exponential functions. Okay, so for linear functions, these are characterized by a always constant growth rate. Constant. Maybe instead of saying growth rate, because it could be shrinking, it could be an always constant shrink rate, always constant rate of change. For an exponential, these are always changing. Rate of change. For a linear, this is always going to be always a straight line graphically, and this is always curvy, always a single curve in graphically. Single curve graphically. Okay, so let's see some examples of these in action. Okay, so let's do some linear examples. Your equation general form is going to look like this: y equals mx plus b. Y is just your y value. M is going to be the slope. B is going to be your y-intercept. Okay, so if your equation looks like this form, it's linear. You should never have any powers on x. Never any powers on x, and you'll be linear. So they are a straight line. So maybe some graphical examples of this. Okay, if I'm drawing a XY area like this, this would be linear. Oh, let's do a lot of different colors so it's a little bit more clear. Let's put them in green, like grass. Here would be a linear. Just like here would be a linear. Here would be a linear. And here would be linear. Straight lines equal linear. Okay, that should be the key characteristic that you're looking for when you're doing this type of analysis. If you see a straight line, you're linear. That's it. Okay, really is that straightforward. Now let's see some exponential examples. Exponential examples. So they're always going to have this form. We're going to have y is equal to the base to the power of x. This is the general form. And you should see that the y value eventually is going to get really large really quickly, or you'll see greater rates of change at a certain side of the thing. It depends on your on the signs. All right, so if you see this form, base could be anything. It could be like any number, any real number. No imaginary numbers on exponential functions. If you don't know what that is, don't even worry about it. But real numbers only. Okay, so graphically, they look a little something like this. Now there is not that much variation on what these might look like. So an example of one, maybe let's do it in red, like strawberries. You might have them looking like this. You might have them looking like this. And in the other direction, I'll do it in purple. You could reflect it this way as well. Or this way. Okay, so what are some key characteristics that we can kind of see from here? Is that there's always one flat side and one curving up side. Flat side and one curving up/down, because it could be curving down, side. Okay, now the flat side will approach a horizontal asymptote. Flat side approaches horizontal asymptote. Okay, so these are the key visual characteristics that you should be looking for when you're dealing with exponential functions. You should see one curving up or curving down side and one flat side of the graph. And if you see that, it is most likely going to be a exponential function, and you definitely want to see the horizontal asymptote. That's where the flat side is going to approach, but the flat side is never going to get to that horizontal asymptote. It's just going to approach there. Okay, it's never going to quite get there. It's going to get very close, but never quite there. Okay, now some real life examples of linear and exponential functions in some real life situations is, well, maybe a linear function is that we are given a weekly allowance of $5 per day. So every day we're getting 5. So an example of this is like our total money is a linear function if this is the case. So every day it's 5. So we would follow this form. Y would be our total bank account. X would be the number of days passed. M would be 5 because we're increasing by 5 each time. And B, that's our y-intercept. In this case, is how much money you would start off with. Okay, so a graph of this function will look something like this. This would be your B value, X, Y, and the slope of rise over run is equal to M. So that's the slope. And in this case, with that allowance example, it'd be 5. Okay, so this is a fairly straightforward example of how we can see this in action. An exponential function in action could be something like compound interest. Okay, so every day that passes, I'm getting an interest amount, or my money is multiplied by, well, if you're really lucky, it could be something like 5%. So you get a 5% increase on your total money every time that you have a passing day, if you're for those type of things. So in that type of case, like every day you're going to have a multiplier between your previous number. So that is going to follow an exponential curve, because here to get to there you are times base, and times here we multiply by base. So the larger the number that you're currently at, when you multiply by base, you're going to increase faster. That's why you see like an accelerating growth rate. Okay, so this is, I would say, is a fairly complete rundown of exponential and linear functions. So the above solution is good. Cool.